Hi, we're in Chapter 5.5, and what we're going to be discussing today are, as our title explains, exceptions to the octet rule. And what we're focusing on is central atoms that can have exceptions to the octet rule. Remember, the octet rule says that when we form compounds, a very stabilizing feature is that 8 electrons surround an atom. What we're going to show is that there are situations in which the central atom may experience an incomplete octet. And what that means is that the central atom is satisfied with less than 8 electrons around it. And we also have situations in which we can have an expanded octet. As the name implies, these are situations in which a central atom is satisfied with more than 8 electrons about it. As a specific example, we're going to go through one in particular. And we're going to begin with the incomplete octet. Now, incomplete octet, there are only 3 atoms that I want you to know that can have an incomplete octet that we're going to study. These include beryllium, aluminum, and boron. And we're going to look at boron as a central atom as a specific example. The other 2, I'm just going to give them to you and you're going to memorize them. But the boron example I really like to discuss. Let's consider a compound composed of boron and fluorine. This would be boron trifluoride. And let's go through the steps of writing a Lewis structure. If we write a Lewis structure, we should remember the steps we go through. We count up our valence electrons. VE, valence electrons. Let's do that. Boron is in group 3A. Boron has 3 valence electrons. There are 3 fluorine, and each of them provides 7. We have 24 valence electrons to work with when we're building our Lewis structure. So, as you recall, for a Lewis structure, the less electronegative atom, in this case, it's going to be boron, because as you recall, fluorine is the most electronegative, and fluorine is never the central atom. Boron sits in the center, and we have 3 fluorines surrounding it. We need bonds, and we'll fulfill the octets of our fluorine. If we take into account all the electrons that we've used, we would see 2, 4, 6, 8, 16. We've used up all 24 electrons. We don't have any more to work with. So what we would do if we were following the rules that we learned earlier, we would try a double bond. Let's try it. Let's do it for the central fluorine. Let's just do it there. We can do it wherever. You might think, oh, this experience resin, but let's not even go there. Let's just check this out and discuss a little bit about why this doesn't occur. We can use formal charge to help us understand why this isn't a good structure. So let's look at this fluorine right here. We'll call this 1, we'll call this 2, and we'll call this 3. Let's look at fluorine 1. And if we account its formal charge, remember it's the valence electrons, 7, minus the assigned electrons, 2, 4, 6, 7. So if we look at formal charge for an argument, fluorine 1 has 0. Let's look at, and that would mean fluorine 3. Notice it's the same as this fluorine. Let's look at fluorine 2. 7, 2, 4, 5, 6. Positive 1. Let's look at boron. Boron has 3 valence electrons. Okay, let's discuss why this isn't a good structure. Fluorine, this guy right here, this one right up here, has a +1 formal charge. Boron has a -1 formal charge. Remember, fluorine is the most electronegative atom on the periodic table. It has positive formal charge. Boron is less electronegative, and it has negative formal charge. This is really not a good structure. Formal charge helps us to explain why we don't expect this to occur. And what we get is we get a situation in which boron is surrounded by 3 fluorine, and each of the fluorines would have octets around them. And boron is happy with 6 electrons around it, and that's what we mean by an incomplete octet. Boron is one of the exceptions to the octet rule. Aluminum behaves very similar to boron. Aluminum also only needs 6 electrons around it. Beryllium is another example of a central atom that is happy with an incomplete octet. Beryllium only needs 4 electrons around it. So this is a description of central atoms that are happy with an incomplete octet. You need to know beryllium, aluminum, and boron. So boron, as we said, is happy with 6. Aluminum, satisfied with 6. Beryllium, we'll discuss more about it when we get into geometry, is happy with 4 electrons about it. These are the 3 you need to know for exam 2 coming up. As I said, we also have situations in which we have central atoms that can have an expanded octet. So let's discuss a little bit about atoms that can have an expanded octet. And there are certain atoms that follow this particular rule, and we'll discuss them in some detail. Expanded octets. Again, we're focusing on the central atom. Expanded octets are found for central atoms that are found in the periodic table in period 3 or greater. So central atoms, and these central atoms are in period 3 or beyond, period 3 or greater. And there's 2 debates right now that sort of aren't completely well understood as to why these central atoms can have expanded octets. They have the ability to be happy or satisfied with more than 8 electrons about them. 2 arguments that sort of are being tested experimentally. First of all, size. When we get below period 3, period 4, period 5, and so forth, remember one of the trends we see going down a group as we move down the periodic table is that we get larger atoms. Being larger, they can accommodate more electron density about them. That's one argument. Another argument is that elements in period 3 or beyond, period 4, period 5, and so forth, have d orbital accessibility. So these are 2 current arguments as to why some elements in period 3 or beyond can have what we call expanded octets. We're going to show when we get into some geometries that expanded octets are found even in elements that are in a noble gas group. And we'll discuss a few of those a little bit later. Let's go through 2 examples of elements that that are taking up the central position that have expanded octets and how we can identify them. Let's look at one particular compound, phosphorus pentachloride, PCl5. Now, if we go through the steps for writing the Lewis structure for phosphorus pentachloride, we would go through and write down the valence electrons that are available to us. Phosphorus has 5. 5 chlorine, each of them have 7. We have 40 electrons to work with. So right now, this is a lot of electrons. Let's put our phosphorus in the center, and let's surround it with our 5 chlorines. We need bonding. And now we need to fulfill the octets of our surrounding chlorine atoms. And we should recognize that phosphorus has more than 8 electrons around it. And that's the only way to explain it, is looking at the situation in which we can have an expanded octet. Also notice phosphorus is in period 3. So that meets our requirement for an element that takes up the central position. If it's in period 3 or beyond, we do get situations in which an expanded octet can occur. Doesn't always occur, but it can occur. Let's look at another situation. This is an ion, a polyatomic ion. This is the iodine tetrachloride ion. Kind of a cool name, ICl4. It's a polyatomic ion. It has a negative charge. Let's write the Lewis structure for it. We take into account our valence electrons. Iodine has 7. There are 4 chlorine. Each chlorine also has 7. And it's a negatively 1 charged anion. Negative 1 charge tells us we have 1 additional electron. We have 36 electrons to work with. I wanted to go through this example because we do have to add another step to how we assign Lewis structures if we consider this situation. Iodine sits in the center, and we're surrounded by 4 chlorine atoms, and we need to have a bond. And next, we need to fulfill the octets of our chlorine. If we take into account how many of electrons that we've used, we would see that we have used up 32 electrons. Four electrons remain. So when we get to this step in writing a Lewis structure, when we have electrons left over and we have an atom, a central atom that's in period 3 or beyond, we should recognize iodine is in period 5. Only the central atom gets the additional electrons that we have left over. In this case, iodine, being in the central position, gets the leftover electrons. These are associated with the iodine. And this is the Lewis structure we get for this iodine tetrachloride ion. Some people like to draw little lobes here to let you know that it's on the iodine. I'm okay with that. You can do that as long as they're not on the chlorine. They're on the central atom. So that's it for exceptions to the octet rule. Our next lecture video will be reviewing a little bit about bonds, and we're going to look at single, double, and triple bonds and the properties associated with them.